Welcome to our presentation on principal components analysis by Lindsay, Ryan, Karine, and Ben. We're going to start with the overview with Ryan.
So usually when we take a data set and want to do some kind of analysis on it, we're interested in explaining some kind of variation. But the problem is the variation in the data matrix is spread unevenly across the variables. Some have much more than others, and often they co-vary in combinations and unpredictable patterns. And because these patterns of covariation could be complex, it's hard to explore them graphically or by pairwise tests like correlation. So it would be useful if we could extract as much of the variance we're interested in as possible and distill it into fewer variables so it'd be easier to deal with. And principal components analysis, luckily, is a method of doing just that. To put it more formally, we need some means of creating composite variables that have maximum variance and minimum covariance with each other, so they act like dimensions in a coordinate system. In linear algebra terms, we need to define unit vectors that maximize the sum of squares of their product with the data matrix, and it can be shown that these vectors are the eigenvectors, which can be derived from the correlation or covariance matrix of the data matrix, and for linear algebra reasons are guaranteed to exist and to be orthogonal to each other, so they have zero covariance. And so if we just multiply the data matrix by the first principal component or the eigenvector associated with the highest eigenvalue, then that resulting vector will be the best possible one-dimensional summary of its total variance. And if we want to keep going, we can just find that we can just do the same thing for the next principal component, which is the eigenvector associated with the second highest eigenvalue, which will be the second best such one-dimensional summary purely of variance not extracted by that first eigenvector. And if we kept going with all P principal components, then we could transform the entire data set to this new coordinate system. But in most cases, we can get most of the variance in just a few components, and so distill these patterns in the data set into a simpler and more manageable form.
Taking a look at the benefits and cautions, some of the advantages of using PCA can help eliminate multi-collinearity, which is a good thing. It improves visualization, helps to overcome overfitting. It summarizes sets of variables with different scales, and it has stable coefficients. Some disadvantages can be the scale sensitivity. Unlike linear regression, results differ dramatically depending on variable scaling. And so also, it can result in overlooking some of the combined explanatory variables. It detects only linear relationships, and it's not as efficient in big data, so it has some difficulty with it. There's no hard rules to say how many components to choose. So generally, it just stops at the point of diminishing returns for variance added with additional components. So the more you add, the more that it stops. Some of the assumptions and pitfalls of PCA are that it's best suited when the data set contains many variables of at least 150 observations. PCA is helpful when multi-collinearity exists between the data because it helps to eliminate it. It assumes that the principal component with high variance should be the focus, and then the lower ones should be disregarded as noise. PCA can be sensitive to outliers because variance and covariance are sensitive to outliers. Next, we have Ben.
Performing full PCA on a dataset identifies all of its principal components. Principal component variables will contain the total variance of the dataset. While predictor variables in a dataset may be intercorrelated, the principal component variables will not be intercorrelated at all. This is guaranteed by symmetric matrices' orthonormal eigenvector properties. Principal component variables will be recombinations of predictor variables, and the number of principal component variables will always be less than or equal to the number of predictors. Principal component variables are described by the amount of variance they represent, usually in terms of percentage of the data's total variance. Principal component variables are typically numbered in order of decreasing total variance.
We're going to have Corinne go over the example.
So in order to apply the PCA, we created an example made of height and weight variables from 6 individuals, men. Height is in centimeters and represent the X value, weight is in kilograms and represent our Y value. So what I basically did, the first step in order to calculate PCA is to compute the mean. So that meant that I had to add each individual height and divided by the number of individual, which is 6 in this case. With that, I was able to obtain 179.17 for height and 95 for weight. Then the second step was subtracting the mean from my data. So for example, let's say the first row, 178 for the first individual. I subtracted it. The mean 179 and obtained -1. Repeated the same process for the weight. So 94 minus 95, which I obtained also -1. The third step was to compute the covariance matrices. So in order to do that, I had to calculate 1, the variance, and 2, the covariance. So the variance is with the difference that I obtained before. I just had to square them and add them together and divide it by the number of individual -1, which is in this case 5. And I obtained for height 3.37 and I obtained for weight 1.2. So in order to do the covariance, I just had to multiply each differences for each individual and then add them together. And with that, I was able to get 0.8. So this is, as you can see there at the bottom, this is the covariance matrices that we were able to obtain from those data sets. The next step consisted of calculating the eigenvalue of the covariance matrices. So in order to do that, I had to follow a specific equation, which is here, determinant. So the determinant of the covariance matrices minus lambda, minus the product of lambda times the identity matrix. So I will go back. So as you can see, this is our covariance matrices here, and this is the product of the identity matrix times lambda. And with that, I was able to get a new matrices made of those numbers. So now in order to calculate the determinant, I had to do the product of the diagonal of this diagonal times the product of this diagonal, which is with that, I obtained this quadratic equation, which is lambda squared minus 4.57 lambda plus 404. And with that equation, I solved for it and I obtained the 2 eigenvalues, which is 3.63 and the second one is 0.94. After that, I had to calculate the corresponding eigenvectors of the covariance matrices. So in order to do that, I had to follow this specific formula. I'm going to show you, which is multiplying the covariance matrices with the X and the Y, and set it equal to the eigenvalues that we obtained from before and multiply it with, again, the new matrices made of, the matrices made of X and Y. With doing that for the 2 different eigenvalues that we obtained from before, I obtained new equation and I solved for them from the previous slide. When I solved for them with the first eigenvalue, I was able to obtain 0.33 x equals y. So, and I did the same thing for the second eigenvalue. I obtained -3.1 x equal to y. So now I had to create the matrices. In order to do that, I went for the simplest matrices that I could think for. So I plug for x equals 1, you obtain y equals 0.33 for the first eigenvalue. So this is the matrices right there. And I did the same thing, repeated the same process for the second eigenvalue, plug x equal 1, and then for y, it's negative 3.1. So now the next step for me meant to normalize the eigenvectors to unit length. So what that meant was I had to divide each value by the square root of the sum of the squared values. So with that, I obtained a new matrix. So this one, if you do 1 divided by the square root of 1 squared plus 0.33 squared, you obtain 0.95. I repeated the same process for each individual value. So as you can see, those are the new value that I obtained. With that, I could now create the eigenvectors of our covariance matrices, which is right there, 0.95, 0.33. So now the next steps meant to calculate the principal component analysis. So what that, which was basically I had to multiply the eigenvectors that I obtained from before with the center data that we obtained. And with that, I obtained PCV of 1 and PCV of 2, which are the new transform data. So those are our data, our principal component scores, and that we're able to obtain.
Right, and now we have Ben, who's going to be interpreting the results for us.
Now let's interpret the results of our example. The predictor's height and weight have been transformed into principal component variables, which are called PCV1 and PCV2. Notice that the values in height do not correspond directly to PCV1, and likewise for the values in weight in PCV2. Because the height and the weight have covariance, the principal components extracted from them will never be height and weight exactly. Principal component variables must be orthogonal to one another, thus having zero covariance and correlation. On this slide, I've colored the values of height and weight relative to their position about the mean. Height and PCV1 somewhat line up. A value below the mean in height leads to a negative number in PCV1, and a value above the mean in height leads to a positive number in PCV1. PCV1 likely has all or much of the variance contained in height, along with the covariance of height and weight. However, weight and PCV2 do not line up very well at all. PCV2 likely has all of the remaining variance of weight not shared with height. However, notice the same coordinates in height and weight give the same coordinates in PCV1 and PCV2.
Thank you. And here are the references that we used for this presentation.